Hello, this is Mr. Gilmore with the 2.1 Conditional Statements lesson. In this class, we will be proving theorems. Well, every theorem that we encounter is going to be a conditional statement. So let's take a look at what a conditional statement is. We define a conditional statement to be a statement using the form if blank, then blank. We're going to fill those blanks in with some sort of condition. So our example here, if two angles are vertical, then they share their vertex in common. So we're going to be encountering many theorems in which we're going to fill in what those blanks are, and many types of conditionals we will then prove to make sure that those conditional statements are true. In order for us to then fill in those statements with some sort of generic statement, we're going to say if given, then conclusion. So we're going to use the given as the beginning of our conditional, and then the conclusion is what we want to reach, or what sort of statement we want to actually prove then is true. Now, not all conditionals are written in the if-then form. Many are what we call implicit conditionals. So it's simply a statement. It still can be then written in the if-then form, and that's what we're going to be practicing first, because many of our conditionals that we're going to encounter will be implicit, but it will help then to rewrite them into the if-then form so that we know what will be the given and then what will be the conclusion. So an example down below says, I think, therefore I am. Well, we can rewrite that as a conditional in the if-then form. If I think, then I am. Let's take a look at an example here. Linear pairs share a side. So we want to take this, right? This is in the form of an implicit conditional because we don't have the if-then form, and we're going to translate this into an if-then form. So linear pairs share a side. So if, and sometimes you may have to change your grammar around of the sentence. So if two angles form a linear pair, then they share a side. So note that I did have to kind of change some of my grammar around, add some vocabulary to the sentence so it does make sense grammatically when I am reading that. But that's an example of taking an implicit sentence and changing it into an if-then form conditional. Let's do another one. Primes greater than 2 are odd. Primes greater than 2 are odd. So I could say if a prime is greater than 2, then it is odd. And there we go. I take this implicit conditional, transform it into an if-then form. Now, conditionals, when we make a statement, can be true or false. So what makes a conditional statement false? Well, what we have to do in a false conditional is still satisfy the given of the sentence. So we have to make sure that the example that we pick, that it still satisfies the given, but we're going to find that it does not satisfy the conclusion. So if we take a look at this statement here, this conditional, if a number is prime, then it is odd. Well, in order for us then to make this false, we have to find a number that is prime, but that is not odd. And that makes what we call a counterexample to this statement, giving us a false conditional. So this statement is false. Why? Because 2 is a prime number. So does 2 satisfy the given? Yes. But does it satisfy the conclusion? No, right? 2 is a prime number, but it's not odd. And so when we encounter a conditional statement, we have to make sure that our counterexample does satisfy the given, but makes the conclusion false. So let's analyze a few conditionals. Let's take a look at some conditionals, and let's determine, is the conditional true or is the conditional false? If it is false, we're going to provide a counterexample to it, meaning some example that does satisfy the given, but then it fails in the conclusion. So determine the truth value of this conditional below. If two angles are supplementary, then they form a linear pair. Well, this statement I can go ahead and say is false. Okay, because one thing about supplementary angles is they are not guaranteed to be adjacent. Well, linear pairs need to be adjacent. So what I could have is I could have, let's say, an angle here that is 145 degrees, and then I can have an angle over here, which is our 35 degrees, and those two angles are supplementary. But do they form a linear pair? No. So my counterexample is this diagram. It's this figure that illustrates a counterexample to this statement. So counterexamples can come in many forms. They could be a word, they could be a definition, they could be a postulate, a theorem, they could even be a diagram. All right, they could be a number, some sort of value. So there are many ways that we can counter a conditional by giving this example that satisfies the given, but it fails in the conclusion. Let's take a look at another one. Perfect squares are not prime. Perfect squares are not prime. True or false. It might help if you wrote it as a conditional. So you say, if a number is a perfect square, then it is not prime. Well, this is actually true. Okay. You may be thinking, well, what about 1, right? We always argue around 1. Is 1 a prime number? 1 is not a prime number because in order for a number to be prime, it must be a positive integer and it must have precisely 2 divisors. Well, how many divisors does 1 have? It has precisely 1 divisor, which means it does not count as a prime number. But if we think about then all of the other perfect squares we encounter, these have more than 2 factors or divisors that go into them, which then means this statement is true. One more example. No 2 primes have a difference of 2, which means what I'm saying is that if we were to find 2 prime numbers, pick any 2 prime numbers, then their difference cannot be 2. And this statement is false. I can think of dozens of examples. Right off the bat, we have 3 and 5. Their difference is 2. We can have 5 and 7. Their difference is 2. We can have 11 and 13. Their difference is 2. We can have 17 and 19. Those differences 2. And we can keep going. In fact, there is a proof of this that does show that there are an infinite amount of these what we call prime pairs where their difference is of 2. That concludes our 2.1 lesson on conditionals. Be sure to look at the worksheet. There's some more information there. If you do have any questions, please email me and ask. I'd love to help. With that, be good and do good.